listening, then it is very difficult and you will not understand. Even if you have understood, once you go back, you will forget. So all of you, please be proactive and do it. It may be like you may make mistakes, like we all make mistakes, and then we head towards a little perfection side. So please join from your laptop, share your screen and show them. That's the way you have to learn. So now I'll start sharing my screen. So we'll first learn the concept of, because all the participants are on a separate level. So to bring everyone to the common level, we have kept this session of correlation. Many of you who have attended any other workshop might find it a little repetition, but just bear with us, because there are many first time attendees also. So that's why we have started with this session on correlation. So I like all of you know that whenever we want to study the association between the two variables, we say such terms like maybe the chi-square or maybe the correlation or something like that. Now, coming to the nature of the variable, it decides which type of association you would apply. So the learning objective of this this session would be, I will first explain the concept of correlation and how this correlation coefficient is calculated in the background. You don't have to calculate it, but how it is calculated in the background. And then in the next session, we'll go for the simple linear regression. Then I'll perform the correlation and regression in Jamovi. And then I will interpret each of these output, because interpretation is very important, and that will help you to have an insight in your data, how your data looks like. And then you have to perform the residual analysis to check for the assumptions of regression. That we'll see in the part 2, like in the second half of today's session. So now let's begin with the correlation. So correlation, I'll be telling the basic concepts, then research questions, the assumptions and hypothesis. That is very important. And in all these inferential statistics, whether correlation and linear regression, there will be a lot of assumptions. And assumptions are important, and testing of assumptions are important, because then you are not going to commit a serious or a grave mistake in your predictive analysis. And then what are the commands and how will you write the interpretation? And then I will be summarizing at the end before we go to the breakout room. So if you see the research questions, like such research questions, if it is there, then you need correlation to answer such research question. Like if I want to know whether there is any relationship between the serum vitamin D level and calcium level, so both these are paired values, means single individual, both these values are there, and both these are the continuous variable. And if I want to know relationship, now if I want to know the relationship between the percentage of marks obtained and the sleep duration, or you can like have attendance obtained and then percentage of marks obtained in final examination, that is again a type of correlation. And then if you want to know whether female literacy rate and infant mortality rate, it is related or not, then again you can apply a correlation. So in all these research questions, what have we seen? That there is a scale variable in both the case, like the dependent or independent variable. Both these variables are of scale variable or continuous in nature, and I want to know whether these two values are associated with each other or not. What do I mean by associated? Means if I increase one variable, what is going to happen? How the other variable behaves? It is, does the other variable also increases, or it has got no effect, or it decreases? So appropriate statistical test is the correlation, and that is the bivariate correlation, because it is between the two continuous variable. And it is also known as the Pearson's correlation. So now, before we go into the concept of the application and the assumptions, we wanted to tell the concept, the difference between the covariance and correlation. So variance, those of you who have attended our sessions on ANOVA we have tried to tell you the concept of variance. Variance means how the data is away from the individual data is away from the mean. In case of a ANOVA, we define variance like that. And then we calculate the F statistics, that is the sum of square, that we write SSS. So sum of square all that individual values away from the mean. If you square it, add it, and you divide it by the number of freedom, that is the variance. That is in context of the ANOVA or the analysis of variance. Now there is something known as the covariance. So what is a covariance basically? So in variance, there is only single data set and you are measuring the distance from the mean of those individual data set. In case of the two variables, like in case of a bivariate correlation, there are two variables. So now you have to see the covariance, means the variation of one variable in the context of the other variable. And that's the aim of this correlation. So now what is the difference and how we calculate these correlation statistics? So let's see this data set. So you can see here, first focus on this table. So if you focus on this table, what can you see? You can see there are 5 persons and there are 2 variables, exercise in hours and resting heart rate. So suppose this data is there and this is exercise per week. And then this is the resting heart rate, which is the beats per minute. So if I want to calculate the covariance between the exercise hours and resting heart rates to understand how these variables change together, right? So let's see this one. So this is the first person doing 3 hours exercise per week and the resting heart rate is 70. This is the second person doing 2 hours of exercise and the resting heart rate is 75. This is the number of exercises 4 hours per week, resting heart is 68. So how, what can you observe here? Yes, although so it is inversely proportional. Dr. Prashant is writing it is inversely proportional. So yes, as the number of hours of exercise is increasing, the resting heart rate is decreasing. So this is because there were only 5 data sets. So by observation, you can say that the exercise hours, if it increases, the other variable is it is decreasing. So the covariance, we can say that it is in the negative direction. But the next question is, what is the amount of covariance? So how to calculate it? That means we don't have to calculate it again. I'll emphasize the basically the software does that in background. But to have an understanding how the calculations are being run in the background, it is important to know, because then you will understand your data and your result properly. Now, see this exercise. So in this case, you can see that there are 5 people. Again, it is the same number of exercise. And again, number of exercise in hours. So there in all correlation, you will see there are 2 axes because we make a graph also. So there is a x-axis and there is a y-axis. So if my predictor variable is the exercise hours and my outcome variable is the resting heart rate. So definitely the resting heart rate or the outcome variable, it goes into the y-axis. Those of you who don't know, I'm explaining for them. Like in all these correlations, you have got a scatter plot. So in that scatter plot, you keep something on the x-axis and something on the y-axis. So predictor variable is always kept on the x-axis and the outcome variable is always on the y-axis. So in this case, you can say that exercise hours in per week is kept on x-axis and then resting heart rate is kept on the y-axis. Now, how will you calculate the variance in this case of the exercise hours? So if I have to calculate the mean of exercise hours, what will be the mean? So I'll do the 3 plus 2 plus 4 plus 5 plus 1 divided by 5. So mean is 3. Now, if I have to calculate the mean of this resting heart rate y, the mean of this will be 71.6. 70, 75, 68, 65 and 80. Its mean will be 71.6. So have you understood up till this point? The individual, I have just calculated the mean of the exercise in hours per week and resting heart rate Y, again the mean. Have you understood? And why we are doing this? So I am making you the concept, I am making the concept of this covariance clear. And covariance is what? When how these two variables co-vary with each other. So co-vary, that direction we have seen, which Dr. Prashant has written, inversely proportional. That if the exercise hours is increasing, the heart rate is decreasing. But that is only the direction. If I have to know the amount, then what will I do? So I'll calculate the variance of this x-axis. So what I will do, I will deduct this individual, this mean from the individual value. So you can see 3 minus 3 is 0, 2 minus 3 is 1, 4 minus 3 will be again 1, and something like this. So this will be minus 1 definitely, and this is 1. Similarly, if I have to calculate the deviation of exercise hours, what will I do? I will deduct this 71.6 from the individual values. So it will be the deviation of the resting heart rate. This we are just calculating the deviation from the mean. And if you multiply these two values, this will be the value of the covariance. So for covariance, actually, you have to multiply the each variances. And remember, variance is the distance from the mean, the value of the individual value distance from the mean. And how we will calculate it? You have to deduct the mean from the individual value. That is the variance. And then what you do, you only have to multiply these two to have a covariance. So if you multiply these two, the value will be total like this. So in first case, it will be 0. In the second case, it will be minus 0.3.4. Then third case, it will be minus 3.6, then minus 13.6 and minus 16.8. So if you add it, it will be total minus 37. I forgot to put that minus sign. So it is minus 37. But again, if you ask what unit will I put? So this is the total value of covariance. That's how we calculate the covariance. So am I making myself clear, or am I making some sense to you? I don't know. For all those students who are like postgraduate students or probably joining for the first time, is it clear to you? That's why we have only taken 5 data set just to make the understanding clear. So covariance is variance of both the variable when you multiply. That is the covariance. Remember, in ANOVA, we do the sum of square. There we sum it. Here we multiply it and then sum it. So Dr. Tanveer is writing, do we consider signs? Yes, we have to consider the signs also. So in this case, because all is negative, so it is negative. That's why there was a direction now. When one was increasing, the other was decreasing. Remember, I have shown you the exercise. If you increase the number of hours of exercise, the resting heart rate decreases. That's why, Dr. Tanveer, it has got a negative sign. Because whenever you calculate these correlation or covariance, that sign is important because that tells you the direction of relationship, right? So that's why here I have missed it. It is minus 37. Forgive me for that. And that's why this minus sign will tell you the direction. So Shelly has written yes. Kavita has written yes. Okay. So now I'll move ahead. So now coming to the property of covariance. So if X and Y are entirely unrelated, then covariance would be 0. If they don't have any relationship with each other. If X and Y are positively related, then covariance value will be positive. What Dr. Tanveer was asking. And if X and Y are negatively related, then covariance value will be negative. Yes, Dr. Vasundhara. This was the question which I wanted to ask. What will be the unit of covariance then? So just hold on. We are coming to that concept. So in this case, because these are the raw values, but it is not easy to interpret because it depends on the units, and units would be very different. In this case, we have added it, but the units are, one is in hours and the other is in the number. So what will be the unit? So how do we calculate the units of covariance? So in this case, how do we decide for it? So yes, tell me, Dr. Vasundhara, what will be the unit if you have multiplied a resting heart rate, that is a number, and then which is the per minute, and then exercise per like week per hour, hours per week, then what will be the unit? Yes, can you all please write it down in the chat box? If you have multiplied two variables, so how will you do? You have to multiply those two units also. So what will be the unit? Yes. So no one is trying to write beat. Yes, agree. Bharat is writing beat hours into hours. So yes, hours multiplied by beats per minute. That will be the unit. But how to interpret that? Because then there will not be any intuitive meaning of this covariance. So how we do it? And you know that whenever the units are different, and if you want to compare the two different entity, how do we do it in statistics? We just standardize it. And that's how we have standardized this covariance. And this will result in another value, which is known as the Pearson correlation. And this Pearson correlation is basically the total covariance amount, which you have multiplied standard deviation of X multiplied by standard deviation of Y. And that's why it becomes, it has got no unit, because then it gets cancelled, and that's why this Pearson correlation has got no unit. And since it is the multiplication, that's why we call it as a product moment correlation coefficient. If you can recall its name, it is known as the product moment. So since it is the product of two variance, which is the covariance, and you have just standardized that covariance, that's why it is known as the Pearson's correlation coefficient, or R. So now R has got a sign and R has got a value. So now do you understand how this value comes? All of you? Okay, thank you. So correlation is used to determine the strength and direction of linear relationship between the two continuous variable. But again, if you are making categories out of continuous variable, and if you want to calculate the correlation coefficient between categories, like if you just make a category of a serum vitamin D level less than 10 and more than 10, serum calcium level less than 5 and more than 5. Similarly, the sleep duration, if you are making it like less than 6 hours, more than 6 hours, and percentage of marks, again, you are categorizing each and every variable, then you cannot perform correlation. In that case, you will have to go with that contingency, making the contingency table and using the chi-square test. So now there are some underlying assumptions of this correlation. So what are those underlying assumptions? So the first assumption is both the data should be continuous in nature and it should be paired data, means it should be the value of on the same individual. So that's a very important assumption, because many times I have seen students performing correlation on two different statistics, like one on hospital statistics and one on patient statistics. So that is not possible, because if your unit of measurement, one unit of measurement is hospital, another is patient, you cannot apply correlation in that context. So for correlation, the value should be paired. That means it should be measured from the same unit. And the second is there should be linear relationship between the two variables, which we see in this scatter plot. And then there should not be any significant outlier that we check with the box plot. And then again, we need to satisfy the assumption of normality, because that is again important assumption, whether those two data. Otherwise, you will have to go for the Spearman rank correlation, because that is applied when the data is not normally distributed. Coming to the properties of this correlation coefficient, so it measures the strength of relationship, linear relationship, and the sign of correlation coefficient tells you the direction of relationship, like we have seen with the number of hours of exercise per week and the resting heart rate, where it was negative, and that's why we said that it is a inverse relationship. And magnitude conveys its strength. It ranges from -1 to +1, and correlation never implies causation. Now, coming to the interpretation of the strength of association based on this correlation coefficient, if the value of this correlation coefficient is less than 0.3, we call it as a small correlation. Any correlation coefficient more than 0.3 but less than 0.5, we call it as moderate. And then more than 0.5 is a strong relation. So remember, this correlation coefficient has got very huge role in the scale development. So those of you who have attended our questionnaire development and validation, there we have all the statistical procedure are performed based on these correlation coefficient, where we used to determine that construct validity, and there we have used like divergent and convergent using these correlation coefficients only. So it has got in today and tomorrow session, we'll only see its role related to prediction, but this has got a very wide role everywhere in statistics. Coming to the linear relation versus non-linear relationship. So these are the two, you can see the towards the left side. So if you focus on this, these are the two examples of a linear relationship. And if you see this, so this is again a non-linear relationship, which is the like a parabola, or this is like a quadratic equation. So this is a non-linear relationship. Now there is something known as the R square, and we'll use this R square in all today's and tomorrow's session, because this R square tells you like one of the criteria for selection of model. Because today we'll not talk much on models because there will be only one variable, but when you have got many independent variables, then you need to select which variable will be used to form the models. And this coefficient of determination, or R square, is one criteria which decides, or on the basis of which you decide which model to keep and which model to reject. So suppose your correlation coefficient between the serum vitamin D and serum calcium level is 0.5. Similarly, the correlation coefficient between the sleep duration and percentage of marks is 0.7, and correlation coefficient between the state literacy and infant mortality is -0.8. So these value tells us the strength and direction of linear relationship. But if I want to know how much variation in one variable can be explained by the other variable, then what you do, like if I want to understand the variation in serum vitamin D level from one person to another person, how it will be explained by the serum calcium level and by what percentages. Similarly, the variation in the percentage marks obtained from one student to another student can be explained by sleep duration, by what percentages, and variation in infant mortality rate from one state to another state can be explained by literacy rate, by what percentages. So it is calculated as R square. So R, again, all these R we have calculated in the previous slides, and you just square it and multiply it by 100. So like 0.5 square, it will be 0.304. So it will be 30.4%. Similarly, the R square will be the sleep duration, and marks percentages will be 49.2, and state literacy and infant mortality will be 64.1%. So you can see that the changes in serum calcium, the changes in the vitamin D level, 30% of the change is due to the serum calcium. Similarly, you can say that the marks percentages is dependent on the sleep duration, and 49.2% of marks percentage can be explained by the sleep duration. So now coming to the null and alternate hypothesis. In case of a null hypothesis, we say that the population correlation coefficient is equal to 0. And in case of the alternate hypothesis, we say that the population correlation coefficient is not equal to 0. So this was regarding the correlation. Now I'll show you the question. So this is the question on correlation. And you can see I have to perform the correlation between the BMI and cholesterol. these two variables. So I'll go to this data set, and this is my data set. So those of you who are new to Jamovi, or I'll just explain in Jamovi, it is a modified version of R. Basically, all the commands which are running in the background is of R. And in this case, it is a dynamic platform. As you can see that if you enter the variable, the values will be here. If you don't enter, it will not be there. And it has got many functions. In the same view, you can see the result or the output, and you can see the input also. That is the data. And data view and the output view, you can see this is the data view. So before I go to the analysis, I'll show you this is the previous data set. We have used this data set in the previous workshops also. So this is the data set of, I think, 193 individual or 183 total number. I don't remember. We'll see the total number of N here, then we'll see. And then this is like the name of the person, the gender. If you see the variables, it is the name, gender, age, the socioeconomic status, and then the BMI score, systolic blood pressure, cholesterol, vitamin D, and cortisol. So this was the overall variable. And then coming to the data set, so I have to perform the correlation. So you can perform correlation in any of the two quantitative variable, but I have to show as a demonstration on the systolic blood, this cholesterol and vitamin BMI. So coming to this analysis, you can see this, click this regression, and then you can see these are the options. Below is the options of logistic regression, where there is a binomial, multinomial, and ordinal outcome. And here it is the correlation, which is the correlation matrix, partial correlation, and linear regression. So coming to this correlation matrix, you can see here. So I will shift these two because here this is the box where I have to move my variable. So it will be like cholesterol and then BMI. So BMI score and cholesterol I'll move here. And then coming to this is the correlation coefficient. So checking the other assumptions. Here in this case, we believe that you have checked these assumptions before. So in this case, assumptions, if I have to check the assumptions, how will I check? Assumptions, for that assumptions, we need to go to descriptive here. So go to descriptive, and what assumptions we said that the data, both these variables. So I will move these two variables like BMI score and serum, this cholesterol. And then coming to plot, you can see that we generally go for the QQ plot for the testing whether they are normally distributed. So you can see that BMI is again, if the individual data point is on this diagonal line, we say that it is normally distributed. This is the QQ plot, and if your number of sample is more than 50, then you apply this. Otherwise, you go for this Shapiro-Wilk statistics, which is here. Otherwise, I would have gone for this normality testing, that is the Shapiro-Wilk test. And then for outlier, here you have to go for this box plot. So if you click this box plot, and we have shown this in the session of descriptive statistics. So you can see these are the QQ plot, and this is the box plot where there is no outlier. So you can just report that there was no outlier. And in this case, you can see there were few outliers, like 5 outliers. So you can just report these outliers. And again, what you can do, you can remove these outliers. And what is the said rule, you first do the removal of the extreme outlier. So this will be like an extreme outlier. And then you can perform the correlation. So now Girish is asking when to look for Shapiro-Wilk and how to do it in Jamovi. So you can click the Shapiro-Wilk here. Shapiro-Wilk is done. It is a objective way of assessment of normality. In case of a QQ plot, you have to do the visual inspection of the QQ plot and you have to make an interpretation. But in case of a Shapiro-Wilk, if you click it, you can see there will be a value of Shapiro-Wilk W. So this is the P value. And if the value is less than 0.01, then you say that this is not normal. So we want our P value to be more than 0.05. But you will see that it is not good for large data set. If the number of sample is more than 50, it is always significant. In that case, if you use Shapiro-Wilk as a method of normality testing, then you will conclude saying that the variable is not normally distributed, whereas the variable is normally distributed. So that's why initially I did not click Shapiro-Wilk because my samples are more than 50. So that's why I have chosen this. Now coming to the linearity. How do you decide for linearity? Although there is an option of scatter plot in the correlation also. So I may use the same option. So you can go with this Pearson correlation, and this click is the report significance. This is the flag significant correlation. This is the total N. If you want the 95% interval of this correlation coefficient, you can click that 95%. And in this case, you will be like doing this correlation matrix. And if you want densities also, then you can have that in the plot, you will have the density. So if you see this, the value of correlation is 0.68. So 0.68 means like it is basically the moderate. Moderate means high correlation. 0.3 to 0.5 was moderate, and then more than 0.5 was high. So there is a high correlation between the BMI and the cholesterol, which is significant. And you can see the 95% confidence interval. It is 0.75, like lower one is 0.59. So 0.59 to 0.75. And if you see this, so this is the scatter plot, and you can see like it is almost linear in nature. So that's the assumptions. So assumptions we have checked regarding the normality, regarding the outlier, and regarding the linearity. And linearity is checked by the scatter plot. Scatter plot, there is an option of scatter plot here in the exploration also. If you click this, then also you can do the scatter plot where you can, like in this case, I had to plot between the BMI. So BMI is the predictor. So I'll put it in the x-axis and cholesterol on the y-axis. And then you can see this is the, so it is almost linear. And if you like form a line, it will be like that. So similar, this thing appeared here also. Yes, this one. So this is the same. So either you can use this here, since it is there in this option, and this is the density. So this one you can skip because generally we go for the scatter plot. So this is the scatter plot. So this is how we see. So now I am only seeing the association between the two. And once I see that there is an association, I'll go for prediction. And that prediction will be your regression. Like if I want to predict the value of cholesterol by the BMI, then, and if I make like any model or any equation, can I predict any individual value or not? So that's how this is the concept of the linear, this bivariate correlation. Now how to write? So you have to include all the assumptions. So I will write here that a product moment correlation was run to assess the relationship between the cholesterol and BMI. Scatter plot showed that the relationship to be linear with both variables, no outlier. Here in our case, there were 5 outliers, so you can report that. And then QQ plot was plotted. And then you can write that there was a significant correlation. So in our case, it was significant, value was 0.668, p-value was less than 0.05. And then you can write the coefficient of determination. So you can just square it, although the coefficient of determination, you will find it in the that predictive analysis or model also. But here, you can just square 0.68. And then it will be like, if you take it 0.7, then 0.49 or 49% will be the coefficient of determination. You can paste this graph and that will be your value of correlation coefficient and the R square, then P value, and then it is the 180. So sample, it is 180 total sample size, which I was saying. That's why we have gone for that QQ plot. So what is QQ plot and its significance? So basically QQ plot is the quantile plot, and it is the plot to test for the normality, where you can see that in the x-axis, so it is the standard, basically how do we do it? It is the residual. So what is a residual? We'll understand this concept. So it is the plot between the theoretical quantiles and the residuals, standardized residual. So QQ plot is quantile plot, and there we plot we see the individual data point, and if the these black, all these points are the individual data point, and if the individual data point is, most of the data point are very much in line with this diagonal line, then we say that the data is normally distributed. And then Damini is asking where to use QQ and Shapiro-Wilk. So Shapiro-Wilk is used when your sample size is less than 50. In my case, if you see the sample size is 180. Can you see here? In my case, it is 180. So if your sample size is more than 50, then you would go for this QQ plot. If the sample size is less than 50, then you will go with the Shapiro-Wilk. So interpretation is the interpretation. Bharat Pant is writing. Yes, it is subjective. No, that's why normality testing has got two different categories. You can test normality objectively when you have got a p-value, and you can test normality subjectively, like histogram. That is again a subjective way. QQ plot, subjective way. But there are objective ways also. Like one of the most commonly used objective ways is the Shapiro-Wilk. Another is the Kolmogorov-Smirnov, like KS test. There's another which is known as the kurtosis, skewness. All these are the variables where you can see value, and you can say whether the data is normally distributed or not. If you want to be doubly sure, you can use more than one way of doing this. Like in this case, I may plot this histogram also. Like I was saying, histogram. This you can plot this histogram also to see whether the and if you like plot this density, then you can see like over that histogram, this density plot will be there. So you can use more than one way to determine this. So definitely this QQ plot and histogram is the subjective way. Objective ways are reliable, but there is a problem with the objective. As you increase the data, number of sample, it is always going to be sensitive. So they are very sensitive to large sample size, and they will always say that the p-value is less than 0.05. And in case of a Shapiro-Wilk, if the p-value of Shapiro-Wilk statistics is less than 0.05, then you will have to conclude that the data is not normally, whereas it is normal. So that's why it is recommended that if your sample is less than 50, you should not go for QQ plot. In that case, QQ plot will not be a good plot to visualize. So we always recommend, if you have got less sample size, go for objective way of assessment of normality, like Shapiro-Wilk, like skewness, kurtosis, and KS test. Or if you have got like number of samples are more, then you should go for the QQ plot, and we'll see there's again one option which is the PP plot, probability plot, which is not here right now, but it is there in the regression. So once we'll move to regression, you will see that we plot the normality curve for the residuals. So residuals, I'm not introducing that concept now because then you will be confused. I will introduce this concept when we'll move to the linear regression. That is the simple linear regression with only one variable. So is it clear, like Bharat and Kavita and the other participant? Okay. So now we can go to the breakout room now. We can do it once. Those of you who have already done it, you can guide others who are there. And then we would request all of you, those of you who have not downloaded Jamovi, kindly download it and share your screen and show the commands and try to speak simultaneously. And it is requested from all mentors, kindly encourage participants to speak and explain what are they seeing or how they can conclude. You can ask other questions also, like which I have not discussed now, like what to do with the outlier. They have got few options. They can how to tackle with the outlier. So you can discuss those small concepts also in the breakout room. So how many breakout room we are opening? Naveen?
Ma'am, right now four
Okay.
breakout room we are creating.
So you can open 4 breakout room and then assign mentors to each of the breakout room.